Here are some examples of problems about related rates. Problem 1. If a pool of water spread circularly outward with radius changing at 5 meters per second, what rate will the area be increasing when the radius reaches 200 meters? For this problem, first of all, let's just assume that we'll always be using units of meters and seconds, so we don't need to keep track of units. Next, let's write out equations for how each of these variables are changing. We know that the radius is increasing at a rate of 5 meters per second, and let's assume that at time t equals 0, the radius is 0. So we can write r is equal to 5t. Now since we know what the radius is, we can write the area as a is equal to pi r squared. So then we can now write this as 25 times pi times t squared. Now we want to know what dA dt is, because we want to figure out the rate at which the area is increasing when the radius is at 200 meters. So d dt of A is equal to d 25 pi t squared dt, which is equal to 50 pi times t. And from here, we know that t is equal to r over 5, since r is equal to 5t. So we can rewrite this in terms of r as 50 pi times r over 5, which is equal to 10 pi r, and we know that the radius is 200 meters. So the value of dA dt that we want is that r equals 200. So we have 10 times pi times 200, which equals 2,000 pi. So the area changes at a rate of 2,000 pi when the radius reaches 200. However, there's actually a simpler way to solve this problem, which I'll go over right now. If we just start with the equation a is equal to pi r squared, we want to know how the rate that a changes is related to the rate that r changes. So to do this, we can do implicit differentiation on both sides of the equation. This will give us dA dt is equal to d dt of pi r squared, and we can find this using the chain rule to be pi times 2r times dr dt. Now it just so happens that both of these values, r and dr dt, are given to us by the problem statement, so we can plug them in directly here without having to write out an equation for r at all. This will give us 2 pi as a factor in the front, times r, which is 200, we want to know what happens when the radius reaches 200, times dr dt, which is the rate at which the radius changes, given to be 5. And this is equal to 2,000 pi if we multiply it together. So that's a simpler way of solving the problem. Problem 2. Suppose a sphere of water evaporates at some rate of volume per unit time which is proportional to the surface area. Show that the radius changes at a constant rate. Let's call the volume of this water V. We know that the volume of a sphere is equal to 4/3 pi r cubed. And similarly, the surface area we can call A is equal to 4 pi r squared. So we want to relate these two rates. To do that, we can use implicit differentiation like we did before. If we take dV dt, this is equal to d dt of 4/3 pi r cubed, which equals 4/3 pi times 3r squared dr dt using the chain rule. And the 3 in the denominator cancels with this new 3 we have, giving us 4 pi r squared dr dt. However, notice that 4 pi r squared is exactly equal to a, so this is actually equal to a times dr dt. Since we assumed in the beginning that v and a are proportional, we can write, the rate of change of v and a are proportional, we can write dv dt is equal to some constant c times a. Then this equation gives us c times a equals a times dr dt, And if we cancel out the a's, we're left with dr dt is equal to c. So the rate of change of the radius is a constant.